Okay, this month we are going to take a look at this library from Boost called Boost.Lambda2. This is a pretty small library, so it won't take us a long time to go through it. We'll take a look at some examples, and we'll dig a little bit into how the library is implemented just so we can understand exactly how this magic works. So if you go out to the Boost website, you can see the documentation for this library. It's just a single page, and a lot of that is just taken up with kind of the boilerplate declarations of the function operators provided in this library. So what is this library? So if you look in the standard library header functional, now this library declares that it is a C++14 library, and that is because there is one of the functions that they provide these placeholder operators for that is only defined in C++14. All the other functions are defined in C++11. C++14 is 6 years old at this point, so it's not a huge requirement to require C++14. But getting back to the overview of this library, so if you look in the standard library header functional, which is a header that provides adapters and functions for creating so-called functor objects, which we will take a look at when we look at some code, and ways to adapt existing functions to be used as functors. So one of the things they provide is std_bind, and std_bind is a way to say, suppose you have a function that takes two arguments, like plus, right? Plus is a binary operator, takes two arguments, and we want to create a function that essentially does +5. It adds 5 to whatever its argument is. Now you can write such a function by hand, but you can also use std_bind to bind the function stud plus. That's the word plus, not the symbol plus. And you can bind one of the arguments to the constant 5 and leave the remaining argument free. And if you've worked in any kind of functional programming language, you might remember this as so-called currying of functions, where you supply some of the arguments to a function and leave the remaining arguments free. Now, std_bind provides that ability to bind either a placeholder or an actual value to arguments of a function to produce another function. So if you provide specific arguments, it reduces the arity, the number of arguments, to the function. But you can also use the placeholders to, say, supply to create a, say you wanted to create a function that calls plus, but has a single argument to the function that you're creating, and it supplies that single argument as both of the arguments to std+. So you can have a placeholder that says, my first argument, I'm going to pass that to std+ as both the first and the second argument. So it's essentially a function that doubles its argument by calling plus with the argument twice. The supplied argument goes into plus twice. Now, that's all good and dandy, but it gets annoying to have to write std_bind expressions to create compositions of functions. So what Lambda2 lets you do is, instead of writing a std_bind expression and calling std_bind with the first argument being the function stud+ to be the plus operator, and the second argument being the placeholder _1, and the third argument to std_bind being 5, to create a new function object that calls plus with whatever it was called and 5, you can just write _1 plus 5. And that will invoke a little bit of machinery and call stood_bind for you and return the resulting function object with one placeholder and one argument, namely the second argument bound to 5. And most of the basic numeric operators are covered in stood functional, or the functional header from the standard library, but not every single operator was covered. So Lambda2 covers everything that's in the standard library in terms of the functions like stood plus and stood greater and whatnot, but it also covers all the remaining operators that weren't covered by the functional header. So if we look at a little example here, here's a function called countEven. It takes 2 iterators as just, they're conceptually they're iterators, but iterators can, pointers can also be considered iterators. It calls the countIf algorithm with the 2 iterators, and countIf from the algorithm library takes 2 iterators and a functor. The functor is a predicate, so it's a function that accepts a value that is compatible with the values iterated over by the iterators, and it returns a bool. And countIf returns the number of elements in the sequence for which the predicate returns true. So this little function here recalls countIf with the 2 pointers, those are the iterators, and a little lambda expression here written as _1 mod 2 equals 0. Another example of finding the first white space character in a string. So the string is delimited by 2 pointers to constant character, and so we're going to use the findIf algorithm, which takes 2 iterators and a predicate. And here, instead of using the isSpace function from the C-type header, they're just explicitly comparing, saying compare this character. It's either against a space, or it's a tab, or it's a carriage return, or it's a line feed. And again, using a standard library algorithm that takes a predicate. Here they've just expressed the predicate as one of these lambda expressions. This library is a single self-contained header. It has no dependencies. It doesn't unusually for a Boost library, it doesn't even depend on any other Boost libraries. So just the one header file and you're good to go. If we look down in here in the reference, we'll see that we have a bunch of placeholders declared, _1 through _9. Everything is in the Boost.Lambda2 namespace. And then we have support for the basic binary arithmetic operators and unary minus. So that's numeric negation, not bitwise negation. And then we have the binary comparison operators. We have the binary logical operators, so logical and, logical or, and logical not, which is a logical unary operator. We have the bitwise operators, bitwise and, bitwise or, bitwise exclusive or, and bitwise not. We also have the bit shift operators. In addition to that, we have unary plus, which a lot of people don't think of unary plus as an operator that you can override and provide a custom version of, but that is certainly possible. It's not often done because people just think +1 is the same as just 1, so why write +1? But if you're doing something like you have a abstract data type representing a set or something like that, you might have assigned unary operator plus to mean something a little bit different than just than it would mean to say a positive integer. We've got the operator star, so this is the dereference operator. We've got both prefix and postfix increment operators and decrement operators. You've got the compound assignment operators, so add and assign, subtract and assign, multiply and assign, and so on. And then finally there's member function call. So if you have a pointer to a member function, you can call through that pointer by supplying an object and arguments to the function. There's also these so-called projections. We'll look at that when we get into the code example a little bit more. And then there's some detail here on the placeholders. The placeholders are more than just kind of wildcards that get substituted in. The placeholders support subscripting or a function call style, so that as you see here, if you call the _1 placeholder with 2 arguments, it returns the first argument. And you can use them in a subscript style as well. And then that's pretty much the whole library in terms of its call API. If you want to see what those particular functions turn into, you can see down here where they're saying operator plus, binary operator plus, turns into a call to std_bind on the std plus function, and it forwards the 2 arguments given to it. But before we get too down into the weeds of how this library is implemented, let's just take a look at some code here. So I've got first we'll take a look at how you can get this. I'm using VC package, and VC package has this library available as just Boost.Lambda2. And when you use VC package and you use the CMake toolchain file for VC package to configure your build with CMake. Let's get that up here. So up here in my build directory, I've already configured it, but when you run a CMake configuration, it will run the normal VC package install step, and when you do this the first time, it's going to download the library, unpack it, and so on. And then it's going to tell you to do find package boost, and that you require boost, and supply optional components for whatever boost library you might be using. The thing you should realize, however, if you dig into the documentation for boost, that you'll see that they don't supply component names for boost libraries that are header-only libraries. That also means you won't get a boost library target for you to link against, because there's no library to link against. However, it can be handy to have such an imported target so that you can pick up the necessary include directory search settings, so that any components that you have that need to link against this boost library, you will get the corresponding include directories added so that you can find the header files that you're using, because it's a header-only library, so your include search path needs to be set up correctly. Now, one additional wrinkle. Personally, I consider this to be just a dependency omission in VC package's definition for the Lambda 2 package. For find package boost to work at all, you need to have boost config listed as a dependency in VC package. I think, strictly speaking, this is an omission. I think Lambda 2 as a VC package specification should automatically depend on boost config, so that find package boost will work, because find package boost looks for a header file to locate the boost install directory, and that header file is shipped as part of boost config. So if you don't have boost config, if you just have Boost.Lambda and you try to call find package boost in CMake, that will fail. And as I said, you don't get an imported target. So what I did is I did my find package boost to get boost located, and then if that did not create an imported target for Boost.Lambda2, I go and add an interface library. I call that Boost_Lambda2, so there's no chance of it clashing with any library targets that I've got in my own code. I set the target include directories for that interface library to pick up the Boost include-ders, and then I add an alias Boost:\lambda2 to that new target, and that way in my own code I can add an executable, and I can say that my executable links against Boost.Lambda2. Okay, so that's the VC package and CMake machinery out of the way for this library. So this is just a little executable here that generates some random numbers and prints them out. Okay, so prints out 25 random numbers from a standard library random number generator. You can see, and I'm using the same seed every time. So every time we use this code that calls random ints, it's actually going to get the same random numbers, just so we can use that for comparison as we run this different code. Okay, so that's just a little bit of infrastructure. Now, let's take a look at here. I've got a little program. It's going to get those random numbers, and then it's going to call 8 different print functions just to print out some interesting things about them. So if we take a look at the first one, this is not using any machinery from std functional or from Lambda2. This is just showing you how you do this, in a raw loop. So if we just want to print out the even numbers from that sequence, what I'm going to do is loop over the input sequence. I'm going to call this predicate is even, and if the number was even, I'm going to push it onto this other vector, and then I'm going to print out that vector. My second version does the same thing, only now I'm using a standard library algorithm. I'm using copy if, which takes a predicate, and the predicate it takes 3 iterators. So let's just go over the arguments one by one. It takes 2 iterators that are the begin and end of the input sequence that is going to be copied from. It takes an output iterator that the elements will be copied into if the predicate returns true. And I'm using this adapter here from the iterator header. If we look up here, I'm including iterator, and oops, too far. So back inserter is just an output iterator that when you assign into it, it calls pushback on the container that the iterator was constructed with. So this is going to copy from the input sequence and push back onto the output iterator any of the elements for which this predicate returns true. Okay, so we're just kind of evolving this code step by step to show you how we progress from writing something by hand to using standard library algorithms and using Lambda2. We haven't gotten to using Lambda2 yet. We're getting close. So here is another version of this library. Sorry, another version of this algorithm where we're copying, we're locating the even numbers in the input sequence and we're printing them out. I'm calling copy if again, only this time I'm using my own handwritten lambda that returns true when the value is divisible by 2. That's basically turning this little function that I wrote as a plain function, it's turning that into a lambda. Okay, so it's this lambda is providing some unnamed class that has a function call operator that takes an int, and the function call operator body is implemented by this stuff that I put in the curly braces. Now, if I were to use the machinery in std_bind without the assistance of Boost.Lambda, I can call std_bind to create a function object. It's going to bind one of the arguments to std_modulus, which is the % operator. And the first argument is going to be bound with a placeholder from the functional header that's in the namespace std_placeholders. And the second argument will be bound to the constant 2. So now I have a function that takes a single argument, and it does n%2. That's all it does. It doesn't do the comparison. But I can create another bind expression that binds the std=2 function, which is a function that applies operator equal to 2 arguments. The first argument is going to be the result of this modulus function, and the second argument is 0. So I've created 2 calls to std_bind to create a composite functor object that is my predicate, hence the name pred, that I'm going to pass to copyIf. Now that was a lot of machinery there to employ, and it does the job, but it's not something I want to read, and it's not something I particularly find pleasant to write either. So down here we're finally getting to the Boost.Lambda version, Boost.Lambda2. There is also a Boost.Lambda library, but we're not talking about that. That one's a little more involved. We're doing the simple one tonight. So now I'm doing copyIf, and instead of writing that other stuff, I'm just writing _1, which is my placeholder, %2 == 0. So this was nice, short, and compact. It's easy to read. It's easy to write. As long as I understand how Boost.Lambda2 works, or just what it does, rather. I don't need to know how it works, how it does, what it does, but I just need to know what it does. I recognize this as like, oh, that's just a placeholder function that creates a function of one argument. It's going to take that argument, do mod 2 on it, and compare it to 0, and return a bool. Notice I don't even have a return statement here. So we went from handwritten predicate, which we called with copyIf. Well, our first version was a handwritten loop with calling the handwritten predicate. And then we got rid of the handwritten loop by using copyIf and our handwritten predicate. Then we replaced our handwritten predicate with a lambda function. And then we looked at a version using just the functional header and using std_bind and the functions in std_bind. And I think you can kind of agree this was a step back from using the lambda function. The std_bind functionality and the functional header came before std_bind, so this is a C++11 way of writing little functors without having to write your own class or your own free function. And then this is a this is a C++98 way of doing it. This is a C++11 way of doing it. Very simple lambda that was supported in 11. And then down here, we've got our lambda2 C++14 placeholder way of doing it. Now, we can also write functors for other algorithms. So down here, I've written a for each, where I kind of, instead of calling this little print function, which you see here is, a handwritten for each loop that's going over the elements and printing them out. But instead of doing that, I can call the for each algorithm with iterators pointing to the sequence that I want to print out. And I can print out, I can insert into the cout stream using a placeholder expression as I've done here. It's a little bit tricky. If you're very observant, you might have noticed a difference that when I wrote this function by hand, I outputted the label, and then within the loop I was outputting a space and then a value, and then after the last value we get a line feed with no space after the value. But when I did it with the Boost.Lambda2 placeholder expression, in order for this to work, for it to compile correctly, I had to swap it. I had to put out the value and then a space. And not sure if that could be considered a defect in the library or if it's just intentional. The support for the stream insertion operator, it basically only works correctly if the placeholder is the first thing inserted into the stream. So I had to put my little leading space over here in my label, and then I have a space after every element, and then I have a new line, so the very last element has a space before the new line. Little bit wonky, but definitely was simpler up here for the filtering to find the even elements in the sequence. Now, you don't always have just primitive elements in your containers. You have, pointers to objects that you've written and so on. So there's a way to create a placeholder expression that calls a member function. And they call this projection in the documentation. If we go back over here to the documentation, scroll past all these operators, which are kind of all boilerplate the same, and then down here at the bottom there is this additional binary operator, and there's this operator dash greater star, and documentation describes that this operator is intended to be used with projection function objects such as member pointers or member functions taking 0 arguments. And the syntax is kind of ugly, but here they're showing an example of you're taking the address of a member function, and then you're creating a function object that will invoke that member function through an object pointer. And here they're taking the address of a field, like a data member, and doing the same thing. So it's kind of ugly. There's this like dash greater star ampersand, and you can't, you might think like star ampersand, isn't that kind of redundant? Well, it's not, because this dash greater star is a single token, and that thing expects a pointer to member, so the very next thing has to be a pointer to member. So you have to take the address of the member function inside its class. So what that looks like over here, oops, let's get down here. What that looks like over here is I've got an object that has a projection function called get. This object is just a simple wrapper around an int, and then the get function returns the int value that is stored in the wrapper. So if I say _1 dash greater star address of this getter function, that gives me a little getter functor. And then what I can do is I've got a vector of pointers to these objects. I can bind the first argument of the getter to the pointer, and then invoke that member function that calls get, and I get the value of the integer that's stored in this little wrapper, and then I can go mod2 == 0 on that. So here I am, I've got my input sequence of integers, my random integers. I built a vector of object pointers by newing up one object for each one of those integers. Then I am doing a copy if to get the object pointers whose value is even. And then call Boost.Transform to get the integers back out of those objects by calling Boost.Transform with that getter that I created again. So the getter ends up being a projection between the object pointer and the value by calling the projection function that's the member function get. It's kind of a bit of a mouthful, but when you get into these functor object things, the idea of projections ends up being a common idea, right? You've got a data structure that's some kind of container of these structures, and what you really want to operate on is a field within the structures. Well, one thing you could do is you could create a vector of the value type of the field within the structure, copy all the values out of the structure and into this container of values, and then operate on the values. But if you have millions of instances of this structure, you don't want to be copying all that stuff. And what if the values that you're copying are not lightweight? What if they're other object references and so on? It can get messy. So really what you want to do is deal with the projection rather than having to copy these values out intermediate. And admittedly, these examples we're going through here are contrived. And I have to copy out the value just because I want to reuse my little print function that doesn't understand this object wrapper, right? So I'm copying them back out just so I can be lazy and call this little print function. And then I'm just to be nice, even though this is a little kind of example code, I'm deleting the objects that I created earlier so that they don't leak memory. Now, we could do all this again, only this time, instead of calling Boost.Bind on the getter in order to get the value from this object pointer, I've created an operator %member function on the class, and if I just indirect the object pointer, I can then call operator % with 2. So it takes the 2 as the argument to this operator % on the object, and it does computes the modulus on its wrapped value. So here was another way I could find all the object stars for which the value was even, and then again do the same thing. This time I inlined the little projection function instead of storing it in a variable, and we're going to print out all the even numbers that were wrapped by those objects. And so when we run this program, the output from all of these should be the same. And if we do that, so here was our different versions of this code. It's accepting the same sequence of random integers and printing out all the even ones, and you can see that they're all identical. So bunch of different ways to do the same thing, some of which are using Boost.Lambda, some of which are using Boost.Lambda2, some of which are using the machinery from Functional directly, and some of which are using one of which is using a plain old lambda function. Now, this is not particularly egregious, in terms of the syntax that we have to write. It's certainly a lot better than what we did in C++ 98 with Functional. But even though this isn't bad, this is still better. So if we take a look at our next little example here, here I've got some sorting that I'm going to be doing, and let me get my start our project set. Okay, so I've got 3 strings, and they're not in sorted order. And what I really want to do is sort them case insensitive. Let's get this noise out of the way so we can just focus on what we're doing here. So really it should be octogenarian should be first, OCTAG, then octal, case insensitive, OCTAL, and then 1, ON, instead of OC. Now, if I don't sort these case insensitive, what I will get is the uppercase octal will print out first before octogenarian, because capital O in ASCII is a smaller value than lowercase o in ASCII. So let's take a look at what we're doing here. We got a little print helper that's just going to print out the vector of strings. And first we're just going to call stood sort. And stood sort by default doesn't know anything about strings, doesn't know anything about uppercase or lowercase. All it knows is it does a value compare on the elements within the sequence. And so less than operator for stood string, it does case sensitive. It does a case sensitive compare. All right, so it doesn't know anything about how to do case insensitive comparisons. So that'll get us a case sensitive sort. And here we're going to do the same thing, except instead of relying on the built-in instead of relying on the default comparison operator to stood sort, we're going to supply our own comparison operator. And this is one we've written using Boost.Lambda2. We need a function that takes 2 arguments, so we have _1 and _2. And the documentation for stood sort says that it should return true if the first argument is less than or equal to the second argument. And here all we've done is we've just kind of written the opposite condition. Suppose for whatever reason I have a custom data type and it only has a comparison of operator greater. They didn't make it regular, so we don't have operator equal and we don't have operator less, and we certainly don't have operator less equal. But we have operator greater, so we can write the less equal comparison as the not of the greater comparison. So that's our case sensitive sort version 2. And then we want to do case insensitive sort. So if you just think of it simplistically, you say, hey, I can get a case insensitive sort by just taking all the input strings and converting them to uppercase before I compare them. So if we do a stood transform on each individual string, and we copy the characters over by converting them to uppercase by passing them to the toUpper function. So we will make a new string, we'll size it to the size of the input because the size isn't going to change, so we can just avoid repeated memory allocations as we push back onto the copy. Call stood transform, 2 iterators that point to the input sequence, which is the input string, the output iterator that we're going to assign through, which is our back inserter operator that we use to copy the uppercase characters onto our copy, and the transforming function is just stood toUpper. This is guaranteed to be a function in C++ if it's in namespace standard. In C, toUpper may be a macro. So if you're using the one from the global namespace that comes from C, this may not quite compile. But if it's in the std namespace, it's guaranteed to be a function, and it's usually just an inline function that delegates to the macro if it's actually implemented as a macro. A lot of these, is alpha, is lower, toUpper, toLower. A lot of those things implemented from the old C standard library and imported into C++ standard library by including CC type. They implemented them commonly as index into a table by the ASCII character code of the character, and then check some flag bits to say whether or not it is an uppercase character, or toUpper might be implemented as if it is a lowercase character done through the function table lookup, then to do a little bit of bit twiddling that is convenient in ASCII character encoding to convert magically from lowercase to uppercase, or vice versa. But if you use std toUpper, then it's guaranteed to be a function, and this needs to be a function that we pass to std transform, or more specifically a functor object, something compatible with function call syntax, which a function pointer is. But a macro won't work there, so just something to watch out for if you got old C style habits. So this thing, it's going to take a string, create a copy of that string that is uppercase. Then when we call std sort, we can say, hey, take this upper string function, bind the first argument to the first placeholder, bind the argument to upper string to the first placeholder, create another binding on the second placeholder, and then use that to do less than or equal string comparison. So that gets us our first implementation of a case insensitive sort. But hey, maybe we're not happy with the fact that this thing makes a copy, it's doing dynamic memory allocations. Do we really need to do a bunch of fussing around with the heap if we're going to be just comparing strings in a case insensitive fashion? Well, it turns out the answer is no. We can create a functor similar to the way that we compared to strings up here. We can create a functor that's comparing two characters in a case insensitive way by taking the characters and converting them to uppercase before we compare the characters. Then we can use the mismatch algorithm to compare the two sequences of characters that are in the two strings using our case insensitive character comparison predicate. We can find the first place where these two strings differ, case insensitive, and then there's a bit of an edge case where you have to check, did one of the results, one of the strings get exhausted, or were they the same length, or were they of different lengths? There's different conditions under which this mismatch algorithm can end, and so that logic is handled here. And then that gives us a comparison predicate to sort strings that doesn't result in any dynamic memory allocation or any copying of the strings. So we can supply all that to std sort and give us a second implementation of a case insensitive sort. Now, I confess I didn't create this from scratch on my own. I Googled it like every good programmer does, and I scraped it off of Stack Overflow. But I did adjust it so that things were using the placeholders from Boost.Lambda2 so that we could get things a little bit shorter. One thing to note for a lot of these algorithms is that when you instantiate the algorithm, it will copy the functor. So if you look at the signature of these algorithms and the documentation in the standard library, the algorithms take the functors by value. Now, for the code that we've written here, it's not a big deal because these function objects don't actually hold any data. They're just a way to describe a function call operator that gets invoked by the algorithm representing code. So there's no bound data in these function objects, and so copying them around as values doesn't result in any undue memory allocations that we might not like. So if we run this little example program, we see that our initial values were 1 octal octogenarian. That's not sorted. If we call it through the case sensitive sort, both versions we get, as I said, the capital O version. The capital word with a capital O will always appear first because in ASCII, capital letters have lower numeric codes than lowercase letters. But if we call the case insensitive sort, we see that we got OCTAG before OCTAL, and both OCTs came before ONE. And our version with copying of strings came out with the same result as our version with the call to stood mismatch that doesn't copy any strings. So, not bad. Sometimes we can get away with stood bind on existing functions to bind their arguments and use that to compose a larger expression to create a function. Other times, we're doing similar thing here with stood bind there. Other times, it's more convenient to just write a simple expression, combining the placeholders into a larger expression. I don't want to have to write that out as explicit calls to stood bind. You might think, why couldn't we do something like this? This would be handy. Why can't we write this? That would be nice. Why can't we just do that? And you can see from my red squiggles right away, the reason we can't do that is because this thing, upper string, doesn't have an overload that takes this implementation type corresponding to the placeholder. So there isn't a good way to get away from having to write stood bind sometimes when you're using these placeholders. If I were to write a lambda explicitly, it would look like this. Even though I had to call, and I have to capture upper string. Okay. Even though I had to call stood bind here, still a lot less noise than writing a lambda. And if I were to write out a function call operator, a functor class myself, that would be even more noisy, right? Because I'd have all the baggage of declaring a class and writing the function call operator, and I'd still have all the same stuff that we have here, but I'd have even more extra stuff around it. Now, whether this call to stood bind to create a lambda expression is more readable or straightforward to your team compared to writing an explicit lambda function, I could sort of shorten this up a little bit if I used auto here. To create a so-called generic lambda. That would get a little bit shorter, but maybe I'm using C++ 14 where I can't quite, or sorry, maybe I'm using C++ 11 where I can't quite use auto lambdas. The lambdas got more and more generalized over time in various versions of the standard, and to be honest, I'm not sure exactly. Maybe you got const auto ref in C++ 14, right? But point is, although clearly this version using the lambda expressions is less tokens and shorter and more succinct, if your team has never seen stood bind before and they're just unfamiliar with the idea of like binding arguments to functions using placeholders from the functional header. Maybe they just don't have they're not comfortable or familiar with a functional programming oriented background. This explicit lambda might be more of a win simply because it's at the right comprehension level for where your team is operating. So just because something is available doesn't mean you should use it. You got to find out what works best for your team. And I'll confess, like, even though I understand what this is doing, I'm not particularly happy with that, but it does avoid the memory copies, and that might be the fastest way to go in terms of performance, because it's avoiding that extra heap manipulation and all that stuff. But not saying I think this is like a big step up in readability. Might be the kind of thing where I would pull this out into a named function, and then I would have that as a predicate that I pass into std_sort. Okay, so let's look next at so common places in the standard library where predicates or binary operators have to be supplied is, when you're working on algorithms with containers. So for instance, the for each algorithm, we don't use for each algorithm much anymore now that we have range for loops in C++, but you may still have times where it is handy. But for each basically applies a function on each element in a sequence. Transform, again, you may find that you're just writing range for loops instead of writing transform, but transform applies a function on values of an input sequence to compute values that are inserted into an output sequence. Accumulate an algorithm comes from the numeric header. It's not in the algorithm header. But accumulate is useful when you are walking over a sequence of values and you're computing some kind of tally for each element in the sequence, and then you're doing an accumulate operation of that tally that you computed for each element and using it to calculate some kind of running total. Usually the accumulation operation is addition, but it doesn't have to be. It could be any function that you want. And then you get back from the algorithm that total that you computed. Inner product, if you've taken any kind of like vector calculus or physics, you might know that as dot product, but inner product is you take two sequences. For each of the corresponding elements in the two sequences, you first compute a product by taking the two values and putting them into a function that computes a product, and then you get a value out from that. And then the results of all the products of all the individual elements in the sequences are accumulated through a summing function. Now, it's called a product and a sum function, but really they're just arbitrary functors. They don't have to compute a multiply operation and an add operation, although that is the most commonly used form of the algorithm. So if we take a look at these, how we might do that with these placeholder expressions. So here I've just got a fixed array of size 4 of integers, which I'm using the iota algorithm to fill them up. So iota starts filling the sequence at whatever this value is, and then it increments the value once for every element it writes. So I'm going to end up with 1, 2, 3, 4 in this array. And then I'm going to call for each. And the interesting thing about for each is that the function is invoked on a reference to the value in the sequence. So for each can modify the sequence in place. So here I'm using the multiply assignment operator from the Boost.Lambda2 placeholder support. So I'm going to start with 1, 2, 3, 4. Then I'm going to take each element, multiply it by 2, and when I print them out, it should say 2, 4, 6, 8. Transform is similar, except it doesn't modify the sequence in place. It has an input sequence and a destination iterator. And here I'm taking the input value represented by this placeholder, and I'm adding 2 to that value. So I start out with 1, 2, 3, 4, and then I'm going to end up with 3, 4, 5, 6 from transform. Accumulate. Here what I'm doing is I'm imagining that I have a bunch of stood strings, and what I need to do is accumulate the total size of all the strings plus their terminating null character. Suppose I was going to write these stood strings to some kind of buffer, and I needed to know the total size of the buffer needed to allocate, that I would need to allocate in order to hold all the strings plus their terminating new line character. So one way to do that is to walk over the container of words and call stood string size on each element in the sequence of words to get a sequence of string sizes, and then I can accumulate all those string sizes. So the function supplied to accumulate takes 2 arguments. The first argument is which one is it? Which type is it? The first argument is the first argument is the value in the sequence that's being iterated over. The second argument is the current running tally that's being accumulated. So I'm iterating over the sizes. So I'm taking the size, I'm adding the existing tally, and then I'm adding 1 to account for the null byte on the string, and print those out. Here I'm doing the same thing, only this time I'm avoiding the computation of that intermediate container that contains just the sizes, and I'm calling stood bind of size to argument 2, and I guess I had it backwards. Argument 2 is the value from the sequence, and argument 1 is the tally. So I've created a little functor that is binding to the size member function on stood string, and then I'm binding that member function to the string, and calling it so I can get the size of the string plus my current tally plus 1. So this time I'm doing the same accumulate I did before, only this time I'm not doing it with any intermediate container that is the sizes of the strings. And then inner product, this is the most complicated ones because we have 2 functors here. We have the product functor and the summing functor. This is just a goofy example. It's not meant to be any kind of realistic thing. But my 2 sequences are a sequence of stood strings and a sequence of C-style string literals. So null, in this case, they're const char stars, but they're null-terminated C-style strings. So my product function is going to call stood string size on the first argument, which is the stood string. And it's going to call strlen on the second argument, which is a C-style null-terminated string. And then I'm going to add 1.0f just to get this whole thing converted to a floating point, just to demonstrate that the value returned by this product function doesn't have to be the same as the value returned by your summing function, because we're going to take the elements pairwise, apply the product function, return a value, and then that value is going to be passed to the summing function, and the type of the input argument to the summing function and the type of the result of the summing function don't have to be the same. So here I wrote my little summing function as a lambda, and I'm taking that floating point value that was returned by my product function, I'm multiplying it by 3.5, and then I'm static casting that to an int, and then I'm adding it to my running total. So my running total starts at 0. This is my sum predicate, and this is my summing functor, and this is my product functor. Now, you might ask, why didn't I write this summing functor using placeholder expressions? And the answer is that if I say auto sum is the first argument plus the second argument times 3.55f, when I compile, let's bring this over so you can see that. When I compile, I get a warning about conversion from type 1 to type 2, possible loss of data, where one type is a float and the other type is an int. So what's happening is the type of argument 2 is a float, so this is a float times a float. That's fine. But then we add it to an int, and the type of the expected return type of that summing function is int. So it had an implicit conversion from float to int, and it gives me a warning about that being a narrowing conversion. And that's because we can't say, we can't do this. This doesn't work with these placeholder expressions because static cast, there's no overload of static cast that takes the type of this placeholder expression here. So we can't quite silence the warning if we do it with a placeholder expression for the summing function. So this is just another reminder that just like we couldn't call size with an argument of _2, we had to call stood bind of size. Not every expression that you can write is an expression that you can write as a placeholder functor expression. And so anything involving casts, even if you did a C-style cast, it also wouldn't work. Anything involving casts or other operators or functions that aren't supported in this list of functions that are described in the documentation, these are the only things that are supported. So I couldn't call this size function, stood string size, with _1. It doesn't know how to do that. I have to create some kind of a functor and then bind that functor. I could have created, I could have said caster is, well, it wouldn't, I can't, this isn't really a function. I can't call, I can't treat it like the member function expression that I'd written up here with stood string size. The only thing I could do is kind of bind it up in a lambda, which I'm already doing, so it wouldn't make things any simpler. So if we take a look at the output of this program, you build it because I was editing. Okay, so take a look at the output here. When we did the for each, it was given 1, 2, 3, 4, and it came out with 2, 4, 6, 8 because it was multiplying each one by 2. When we did transform with 1, 2, 3, 4, it was adding 2 to each element, so it got 3, 4, 5, 6. When we, let's get rid of this and scroll up here so we can see the two side by side. So accumulate was printing out the sizes of these words, and that's 4, 4, 1, 4, and that's what we got here. And the total size was 17, which is 12 plus 3 plus 1 byte for each of the 4 strings. So that's 12 plus 1 plus 4, which is 17. And when we did it the second way, we used the same words. The words were once upon a time, and we still got a total size of 17. Only that time we did it without making an intermediate data structure that was the sizes of the words. When we did inner product, printing out several things for that one thing here. So here's the 4 input nouns, the 4 input adjectives, and this crazy computation ended up with a value of 139. Now, again, that's a contrived example, but I just wanted to show you, how some of these algorithms accept multiple functors to apply them in different locations of the algorithm. So, what did we learn from all this? Well, what we learned is it's handy when we're doing some simple computations that can be easily written as an expression. It gets a little bit noisy and ugly if we need to do more complicated things. It might be just more straightforward to write a lambda instead of calling Boost.Bind. The other thing that we haven't commented on, except it kind of was implied when I said that these function expressions don't capture any state, so when they're copied around as objects, there's no data being copied around. If you have state that you need to reference, particularly mutable state, that can be tricky with these standard algorithms because, as I say, they copy the function objects around. So if you're dealing with mutable state in your predicates or in your transforming functions, your binary operators that you're supplying to these algorithms, you have to be very careful about managing that state in such a way that as the function object values themselves are copied around, the state is correctly maintained. There's no way to really capture state and have that state be modifiable here in Boost.Lambda2. The idea behind the functional header and Boost.Lambda2 is to write purely functional expressions, and by purely functional I mean a function that when you execute it, it has no side effects. So that rules out modifying any state at all, because that would be a side effect. In terms of capturing state, usually the reason you capture state in a lambda, as we saw over here, not that one. Where was that? Maybe it was down here. Yes. Usually the reason that you capture something in a lambda is so that you can either reference that data member or you can reference a function, and the function is not at global scope. Maybe it's a member function, so you have to capture this. In these lambda expressions usually handle that by calling Boost.Bind, and therefore there's not a need to try and write any kind of capture expression. But if you're capturing, and you don't need to capture data that you're mentioning, because it ends up getting it ends up getting captured as an argument into these bind expressions. Now, that can mean that, unlike with a lambda, where you can capture by reference, so as the lambda is executing, the thing that's being referenced might be changing, and so the lambda, as it's executing, will get access to the new data because it's captured the name by reference instead of by value. Whereas with the Boost.Bind and the lambda expressions, everything is a copy. So at the time that you create the lambda expression, that's when the data is copied in there. There's no way to say capture it by reference. It's always captured by value. So any of the arguments that you supply from local variables and whatnot, they're always captured by value, and they don't change. And again, this is because we're operating in a kind of functional programming paradigm where we're writing functions that are free of side effects, and they're interacting with the environment through not through references, but through values. So does this library eliminate the handiness of writing your own lambda expressions? No. But when you're doing simple expressions, simple transformations, adding to, multiplying to, things like that, projection functions, using the shortcuts provided by the lambda2 library can make things a little bit more concise and just kind of eliminate, even though a lambda function is less boilerplate than writing your own functor class, using a lambda expression is even less boilerplate than that, and it still preserves readability and makes things nice and clear. So it's handy for those situations.